Okay, so the topic that we're going to discuss now is the applications of Gauss's law, and we already know that what is Gauss's law. Gauss's law says that the flux through an enclosed surface is 1 by E naught times the total charge enclosed in it. So it deals with the closed surfaces, and always remember that. So in the application of Gauss's law, we will also deal with the closed surface, and if we won't find any closed surface, then what we'll do, we will create our own closed surface, and that closed surface will be known as Gaussian surface. So the first application says that we have a hollow charge sphere and we have to find the electric field or the flux at its center or at the region where it is hollow. Fine. So the hollow charge sphere, you can think of it as a ring. Suppose I have a ring here and I have to find the flux at its inner region. And this sphere or the ring is charged positive on its outer surface. So suppose that I can find its electric flux at point P, and this is my point P. Suppose I'll find the electric flux at this point. So what I'll do to fulfill the condition of Gauss's law, I'll create my own surface that will wrap this point P, and that surface will be known as Gaussian surface. And in this case, the Gaussian surface is in the form of sphere. Fine, this is our Gaussian surface. And our point where we need to find the flux is also present inside that surface. Suppose that is my point P. Okay. So as we know that we have the Gaussian surface and the point where we need to find the flux is also present in the Gaussian surface, then we can do something with that. We can say that what are the charges that are present inside the Gaussian surface. So how many charges are enclosed in the Gaussian surface? As you can see, there is none of the charge present in the surface because all of the charges are present outside of the sphere that we have, and none of the charge is present inside the Gaussian surface. So if you write our equation of flux, that is phi equals q over E naught, we can say that none of the charge is enclosed in our Gaussian surface, so q will be 0. And as q is 0, so the whole flux of that Gaussian surface will be 0. And if the flux to the Gaussian surface is 0, so we can say that there is no flux present inside a hollow charged sphere, or the electric field in the hollow charged sphere is 0. Fine. This is all about the hollow charged sphere and the flux in it. So let's come to the next application. That says that we have a large sheet. Suppose this is our large sheet and we need to find electric flux at both of its sides. Suppose we need to find the electric field at point P on the left side and at point this P on the right side. So what we'll do, we'll consider only the hand side, and then once we have calculated the electric field at this point, then the electric field at the right hand side will be the same. So we'll just add them together. So again, we have to find the electric flux or the electric field at a certain point, and that point is P. And in case of Gauss's law, this point is not present under a closed surface. So what we'll do, we'll construct our own Gaussian surface, and in this case, we have constructed a cylindrical type Gaussian surface. You can see here, this is on the left hand side, and again a same cylinder on the right hand side. So for now, let's just consider the cylinder on the left hand side. Okay, so this cylinder has got four sides. This cylinder, this side, this side, and the side which is present in the in the sheet. So it has four sides. Let me draw it very clear. This is the first side, the second side, the third, and the fourth, which is present inside the our sheet, inside our sheet, and our sheet is present. Suppose this is of my sheet. Fine. So the side which is present inside the sheet will have zero electric field because it is in the sheet, and the electric field is always outwards. It is always present outside uh, of the thing or the particle which is producing the electric field. So if we talk about the surface which is present, if we talk about the side of cylinder which is present inside the uh, infinite sheet, so then we can say that it will have zero electric field. And as for this side and this side, you can see that the area vector of both of these sides is always perpendicular to its surface. So the area vector of this side will be upwards, and the area vector of the bottom side will be downwards. And our electric field is in this direction, as you can see, because the positive charge is producing the electric field. So if I were to calculate the angle between the electric field, our area vector of the top side, so what I'll get what I'll get is the angle 90. And what happens when the angle is 90? The flux is zero. And same with is the case with the bottom side. The area vector of the bottom side is downwards, and the electric field is again is outwards, and the angle is 90. So once the angle is 90, the flux is zero. So we can say that the top side, the bottom side, and the side which is present in the sheet has zero flux. So what remains is this side, this side, because if you draw the area vector of this side, what will end up is the area vector will be perpendicular to this surface, and it will be in the same direction as our electric field. Fine. So the angle is zero, and once I put my angle in zero in our flux equation, I'll get phi equals Ea, because cos of zero is 1. So now I've calculated the electric flux at the left hand side of our Gaussian surface, that is phi equals Ea, and the flux is only because of the of and the flux on the left hand side is only because of this surface, this side of the surface. And I already told you that for the top surface, for the bottom surface, and for the surface that is present inside the sheet, the flux will be zero. So same will be the case on the right hand side. So on the left hand side, the flux is Ea, and on the right hand side we will get the same flux because the Gaussian surfaces are same. Fine. So the overall flux of the Gaussian surface will be phi equals to Ea. Fine. Because we have got the left side of the Gaussian surface and the right hand side. And for the left hand side, the flux is phi equals Ea. And for the right hand side, it will be the same. And when we'll add them together to get the overall flux of the Gaussian surface, we can say that the flux will be 2Ea. So we got our flux, that is phi equals 2Ea, and we know the overall that the Gauss's law says that the flux of the closed surface is the charges enclosed in the surface divided by the permittivity. So we can replace our phi with 2Ea, that is the total flux in our Gaussian surface, and we can replace our charge with the equation of charge density. What is charge density? We can represent charge density with the sign of sigma. The charge density says the is the charges present in an area. Fine. We have suppose we have any type of area, so the number of charges present in that area represents the charge density, and the equation for that is sigma equals q by a. So if I were to assemble this equation, I'll get q on the left hand side and sigma and a on the right hand side. So I can replace my q with sigma a divided with epsilon naught, and I can cancel out the area. Yeah, area quantity can be cancelled, and what I'll be left with is the electric field equals to sigma divided with 2 epsilon naught. So remember the formula again, that in case of large sheet, the electric field is given by the formula E equals sigma by 2 E naught. E equals sigma by 2 E naught. This is the formula for electric field when we are given with the infinite sheet of charges. Fine. And we have derived this equation using the Gauss's law and the Gaussian surfaces. And the Gaussian surfaces in this case was in the form of cylinder. So the next application we have is we are given with two oppositely charged plates, and we need to find the electric field at any point. Suppose that point is, in this case, is P. So again, we are given with a point, and the point is not present in any closed surface. So to use the Gauss's law, we have to construct our own closed surface that is known as the Gaussian surface. And in this case, they have constructed a rectangle as a Gaussian surface. This rectangle is our Gaussian surface, and our point lies in that Gaussian surface. So we will find the flux through this surface, and that flux will be the same at point P. Suppose that point is present in our Gaussian surface and it is point P. Fine. So again, we have got four sides of our Gaussian surfaces, and we'll calculate the flux through each of the sides. Suppose this top side is present inside the material which is producing the electric field. So the electric field at this region will be zero. Fine, because the electric field is always present outside of the surface that is producing the electric field, not on the inside. So as the electric field is zero, the flux will be zero. So that we can say that at top flux is zero. And on the left and the right hand side, and on these sides, we can say that these sides are having the same direction as the electric field, because the electric field is downwards, and the surfaces are also present at the same direction. So the area vector will be perpendicular to them. So the area vector of the left hand side will be, suppose, in this direction, and the area vector on the right hand side will be, suppose, in this direction. And these area vectors are perpendicular to the electric field, as our electric field is downwards, and one of the area vector is along this direction and the other one is along this direction. So the area vector is making an angle of 90 with our electric field. So once we put angle 90 in our flux equation, we'll get cos of 90, and cos of 90 is 0. So the flux at each of these sides will be 0. So we can say that the flux at the top is 0, flux at the left and right hand side of the Gaussian surface is 0. So what we are left with is the bottom surface. We are only left with the bottom surface. As you can see that the bottom surface is perpendicular to the electric field. If I can draw it right here, electric field is downwards and the surface is perpendicular to the electric field. So the area vector of this surface will be perpendicular to it, and it will be along the direction of electric field. So the angle between the electric field, which is downwards, and the area vector of the bottom surface of this surface will also be downwards. So it will make an angle of 0 with the electric field. And once we put angle 0 in our cos equation, our flux equation, what we'll get is flux will be equal to EA. So the only flux in our Gaussian surface is being produced because of the bottom surface. So the only flux we have is because of this surface. So we have, that's why we have phi equals EA and not 2EA as we had in our previous case. Fine, so flux is EA. And again, using the Gauss's law, we can say that flux equals Q by E naught, and we can replace our Q with the equation of charge density, and that is sigma A divided by E naught, and our flux of the Gaussian surface is EA, and both the A factors can be cancelled out, and the electric field will be equal to sigma by E naught. Fine. So we have two equations up till now for the electric field in different scenarios. One scenario is is the infinite sheet of charges, and in that case, the electric field, the formula for electric field is sigma by 2 E naught, and the other one is the electric field between the two oppositely charged plates, and the formula for that is E equals sigma by E naught. The difference between the two, both of these equation is just the factor 2 that is being added in the denominator. So these were the applications of Gauss's law, and we have derived the equations for electric field by using the Gauss's law and the Gaussian surfaces.